IT, who's our last speaker for the day, and he'll be speaking on K-theoretic Hall algebras for quivers with potential.
Yeah, thanks for the introduction and for the opportunity to speak here. So the plan for today is as follows. First, I'll review some basic notions related to quivers. So actually, they all have been reviewed in the previous talk. And then I'll say a few words about some construction, some algebras appearing under the name of Hall in the literature. So once again, this section will have a non-trivial intersection with Olivier's introductory part from Monday. But the algebras will go up to dimension 3 today. And in the second part of the talk, I'll focus on one such class of Hall algebras for quivers with potential that are supposed to locally model this K-theoretic Hall algebras in dimension 3. So first, a quiver is a directed graph, and I'll denote by V the set of edges, E of vertices, E the set of edges, and S and T the source and target maps. And the example to keep in mind for today's talk is the Jordan quiver. So this is a quiver with one vertex and one loop. And given a quiver and a field, we can construct an algebra called the path algebra, which is generated by paths in the quiver, and multiplication is given by concatenation of paths. So for example, the path algebra of the Jordan quiver is generated by polynomials in the loop of the Jordan quiver. So representations of the path algebra can be described as follows. So first, we need to pick a dimension vector, which means that we pick a natural number for any vertex of the quiver. And then we place in any vertex of the quiver vector space of dimension di. And then for any linear map in the quiver, and for any edge in the quiver, we choose a linear map between the source and the target vector spaces. So this choice of linear maps will give us a k-valued point of this affine space. Now, changing the basis of this vector spaces placed in the vertices of the quiver, we get an action of a reductive group, which is a product of GLDVs on this affine space. And the quotient of the affine space by this reductive group is the stack of representations of the quiver. So this will play an important role in today's talk. So maybe keep in mind that it's a smooth stack. So here we just have an affine space modded out by a reductive group, which is very explicit. Yes, so next, Hall algebras. Yeah, so the first construction I want to review, or I want to say a few words about, is the one that most people know under the name of Hall algebra, and in this generality was introduced by Ringel in the 90s. So it starts with a quiver and a finite field, and then it has, so as a C vector space, it's generated by isomorphism classes of representations of the quiver over the finite field, and multiplication and the product between two such representations. It's a weighted sum after all possible extensions of one by the other. So this whole algebra, the whole algebra of a quiver is closely related to a quantum group associated to the Kac-Moody algebra of a quiver. And one precise statement in this sense is this theorem of Ringel and Green. So which says that if Q has no loops, then the spherical Hall algebra, so the spherical Hall algebra is this subalgebra generated in dimension vectors where the sum of coordinates is 1, is the positive part of the quantum group associated to G, where G is the corresponding Kac-Moody algebra. So I changed the slide. Oh, sorry. Can you see that I changed the slide?
We still seem to be on the classical Hall algebras slide.
Yes.
Yes.
Yeah. So this spherical Hall algebra can be categorified using shifts of Perver sheaves. So there is a category whose split Grothendieck group. So there is a category of constructible sheaves on the stacks of representations XD, whose split Grothendieck group is the spherical Hall algebra. And multiplication is defined as follows. It's P lower star, Q upper star, where P and Q are as follows. So first we need to take the stack of B plus C representations with a given dimension D subrepresentation called XD comma E. And then we have a map Q to XD times XC, which will be an affine bundle map. And a map P, which forgets A to the stack of representations of dimension D plus C, which is proper. And actually multiplication for all the other whole algebras we'll see today are defined in a similar manner, just that sometimes it's harder to make sense of these functors. And then actually there is a singular support functor, so that goes from this category CD. So they can be upgraded to D modules with a good filtration on XD. And then by taking the associated grade of that, we obtain a graded, so this is the meaning of the C star here, coherent sheaves on the cotangent stacks. So we know that the K-theory on the left-hand side, so these categories of constructible sheaves categorify the spherical whole algebra. So now Grozhnovsky's proposal was to look on the right-hand side, see whether one can define a whole algebra here, and what is the relation between this potential algebra and the initial whole algebra. So this is the subject of this preprojective or two-dimensional whole algebras. So one takes the Grothendieck group of the right-hand side that I just wrote, and for example, if J is the Jordan quiver, then this is the same as the K-theoretic whole algebra for the surface A2, or in Olivier's framework from yesterday, the two-dimensional whole algebra associated to A1. So there are a couple of natural questions here. So one is, what is the relation between this K-theoretic whole algebra and the initial whole algebra? So what does this singular support map do? And the second one is, what is the relation between this K-theoretic whole algebra and quantum groups? So we've seen that the whole algebra is related to a positive part of quantum groups. So is this the same for this KHA defined using coherent sheaves? And well, so we've learned the answers of these questions in Olivier's talk yesterday. So the answer for the first one is that they are related, and the heuristics is that this KH should be an affinization of the initial whole algebra as defined by Ringo. So a precise conjecture in this sense is the following conjecture that says that for an arbitrary quiver, the KH of the quiver should be the positive part of a quantum group defined by Okounkov and Smirnov. So this is something like an affine quantum group associated to this Lie algebra GQ that was defined by Maulik and Okounkov. And which in general is larger than the Kac-Moody Lie algebra. So next, I want to say a few words about whole algebras for three-dimensional categories. So conjecturally, any Calabi-Yau from any Calabi-Yau 3 category, we should be able to construct a whole algebra, and this should be a categorification of enumerative invariants on that category. So for example, if this category comes from a projective Calabi-Yau 3-fold, then maybe one expects that part of its behavior is determined by a BPS Lie algebra, or that it satisfies something like a PBW theorem, and then the number of generators of that algebra is given by this invariance called Kumar-Vafa invariants of the Calabi-Yau 3-fold, which are related to other counting theories like Donaldson-Thomas or Gromov-Witten on X. So it's very hard to make sense of multiplication in this very general context. So it's not known that these algebras can be defined. However, locally, these algebras should be modeled by quivers with potential. And in this situation, one can construct the whole algebra. So this was, or even a categorification of the whole algebra. So this was done by Kontsevich-Soibelman. So why study this three-dimensional whole algebras in this local case? So as I was saying, they should have a relation with the enumerative geometry, but then also they generalize two-dimensional K-HAs. And not only that, but they also behave in similar ways to two-dimensional K-HAs. So for example, they satisfy a PBW theorem. So maybe the expectation would be that they are also positive parts of some quantum groups. So yeah, so the relation between this one-dimensional, two-dimensional, and three-dimensional whole algebras is written at the end of the slide. Okay. So finally, so now I need to define what is a potential. So once again, this the quiver with potentials will be used to model or is conjecturally model what happens for a general Calabi-Yau threefold. So a potential is a linear combination of cycles in Q. So here it's important that they are cycles, not paths. And the example to keep in mind is this pair, where Q3 it has one vertex and three loops, x, y, and z, and the potential is x, y, z minus x, z, y. So out of such a pair, we can construct an algebra called the Jacobi algebra, which is a quotient of the path algebra of Q by the two-sided ideal generated by derivatives of the potential. So for example, in the Q3W3 case, the path algebra will be the free algebra on x, y, z.
I think we don't see your slide that you're on.
Oh, yeah, sorry. Let me see. Okay. Right now, I think you can see it. Yeah, thanks for telling me. So it will be a quotient of the path algebra generated by x, y, and z mod. So when we take the derivatives of W3, so once again, the example I'm talking about is this Q3, which is a quiver with one loop and one vertex and three loops, and the potential is xyz minus xzy. So the derivatives will give us precisely commutators in these variables. So the Jacobi algebra will be the polynomial algebra in x, y, and z. So now we look at this stack of representations of the Jacobi algebra, JD, and it's not hard to see that this stack can be written as the critical locus of a regular function, the trace of the potential, on XD. So this JD will be inside XD, which is a stack of representations of the path algebra. But it has also this property that it's so also we'll assume that 0 is the only singular value of this regular function. So actually this JD is the locus of singularities of the central fiber, and all the other fibers will be smooth. So for example, in the Q3W3 case, the stack of representations is the same as the stack of torsion sheaves of length D on A3. And this can be written as the critical locus, indeed, of this trace of xyz minus xzy on this smooth stack. Oh, okay. So now the definition of the KHA is as follows. So for any dimension D, we take the Grothendieck group of the category of singularities of XD naught. So this will tell us something about the singularities of the central fiber XD naught. So the definition is that this category of singularities is the triangulated quotient of the derived category of bounded complexes of coherent sheaves on XD naught, modeled out by the subcategory of perfect complexes. So if XD naught were smooth, this category would have been trivial. However, XD naught is not smooth, and its singular locus is precisely JD, this stack of representations of the Jacobi algebra. So, yeah, this will be the measure of our singularities of JD. So maybe I should say a few words on why one would take this derived category, this category of singularities. So this is a categorification of vanishing cycles, and this is what was used by Kontsevich-Soibelman in cohomology, and this is what also what appears in enumerative geometry. So the meaning of K-crit here is just this thing by definition is K-theory of this category of singularities. So one should think of this K-crit as a K-theoretic version of vanishing cohomology. So other nice features of these categories of singularities, so they are they also appear in the literature under the name of matrix factorizations. So we have functor relative for them, and we can use our preferred multiplication to define associative algebra on this whole algebra, on this well, underlying vector space. And yet another property they have is that even if they look pretty hard to compute from the definition, is this quotient of two triangulated categories, there are theorems which say that in some cases they are equivalent to dB-co on some varieties or on some stacks. So this is this dimensional reduction theorem of Isik, and also Orlov has related results. And this kind of result allows us to go from 2 dimensions to 3 dimensions. So for any 2-dimensional KHA, so recall that this was defined using the sheaves on the cotangent stack. We can cook up quiver Q tilde and a potential such that the derived category, the categories of singularities associated to this pair will be equivalent to dB-co on this cotangent stack. So indeed, these 2-dimensional KHAs are a subset of 3-dimensional KHAs. And an example here is that for the Jordan quiver, the pair is Q3 W3. And the algebra is the positive part of UQ GL1 hat hat. Okay, so using frame quivers, we can construct representations of KHA. For example, in the Q3W3 case, what we can do is we can add a new vertex and an arrow from this new vertex to the initial vertex of Q3. And we can choose the stability condition, which says that the image of this framing map generates the dimension D vector space under the action of X, Y, and Z. So then KHA will act on, yeah, and then we also have a potential, the same potential W3 on this space. So KHA will act on the Grothendieck group of these categories of singularities. So here we don't take the full stack, but we take only its semi-stable part with respect to this stability condition I described. And then the singular locus of this central fiber ends up being the Hilbert schemes of points on A3. So we get an action of this KHA on this thing called critical cohomology of Hilbert A3. So also using similar ideas where we frame the quiver and we deform the potential, we can show that for any pair Q tilde W tilde, so these were the pairs for which the KHA ends up being the 2-dimensional KHA. Then the whole algebras will act on K-theory of Nakajima quiver varieties. So the precise example is this one. Yeah, so now I was saying that this 3-dimensional KHAs behave, or they have some properties which are expected of 2-dimensional KHAs. One such evidence is that they satisfy a PBW theorem. So recall that there is this conjecture which says that a 2-dimensional KHA is the positive part of the Okounkov-Smirnov quantum group. So in particular, they are expected to satisfy a PBW theorem. So this was motivation for this theorem. And actually what happens is that a very large class of three-dimensional K-HAs also satisfy a PBW theorem. So the statement is that there is a filtration of the K-HA such that the associated gradient has the same size as the symmetric algebra on the first piece of the filtration. So for sure, as an algebra, it's a deformation of the symmetric algebra. So the relations are something like this. And the first piece of the filtration is given by the Grothendieck group of some natural categories and D inside these categories of singularities. So, and the proof goes as follows. So instead of proving the statement directly in K-theory for a pair QW, we prove a categorical version where the potential is 0. So namely, we find some semi-orthogonal decompositions for this category dB on the stacks XD. So what happens here is that one can find a subcategory which behaves like almost cuspidal part of it, this M bar D, which is admissible inside dBxD, and its complement is generated by analogous categories coming from smaller dimension via multiplication. So, for example, the strategy of decomposing categories of stacks is employed in variation of GIT and things like that by Harper-Leisner and Balafar-Katsarkov. But one issue is that it's a little hard to work with this functor P lower star Q upper star. And the inspiration for the semi-orthogonal decomposition came from work of Spenko and van der Berg. So they looked at categories related to M bar D, which gave them a non-commutative Crepin resolution of singularities of XD, so where XD is the core space of the stack. Once we have such a semi-orthogonal decomposition, so the point of this paragraph here is that this category's M bar D can be described very explicitly. You don't have to worry. So this MR is the weight space of the group GD, and the sum is taken after all weights of GD on RD. So where RD was that affine space defined at the beginning of the talk. So once we have this categorical version, we can actually prove an analogous version for categories of singularities pretty easily. So we can put the potential in the picture, and we can deduce this theorem. So so this also shows that this three-dimensional K-HAs are important when we study two-dimensional K-HAs, because the proof of the PBW theorem for a two-dimensional K-HA. So let's say that this is a quiver that appears in a two-dimensional K-HA Q tilde, and we want to prove a K-HA for W tilde. What we do is we prove a categorical version when the potential is 0, and then we deform it to W tilde, and we get the PBW theorem for this pair that gives us a 2D K-HA. Yeah, that's all.
Okay, thank you very much. Are there any questions?
Yeah, I have two questions. One is about your filtration. Is it just a K-theoretical version of the weight filtration of Ben-Davison, which gives you this BPS-Lie algebra?
Yeah, so it's actually different from that, because what Davison-Meinhardt do, they use the decomposition theorem. And they use the perverse filtration, which comes from this map, from applying the decomposition theorem from the stack XD to its core space. So sure, the factors that appear when one applies this decomposition theorem are IC sheaves, and the first part in the filtration, which gives the BPS algebra, will be given by some IC sheaves. So sure, we don't have the decomposition theorem in K-theory, and also we don't have this IC sheaves for the core space XD, so it's different, I'd say.
Yeah, okay. And the second question, it's a computational one. For you have defined it for quiver with potential, but like cohomological whole algebra could be defined, and even K-theoretical in geometric setup. Yeah, like for surfaces, like in Olivier's talk. Now,
Yes.
can you? What about computations? Can you compute it, for example, for coherent shifts on a curve, not even on the surface?
Sorry, so you mean if I can compute the KH when for
Yeah,
this
you can upgrade whatever.
C times
Yeah,
one?
yeah.
Oh, no, I didn't think about that. So I just thought about this local case.
Yeah. Okay.
Yeah, thanks for the question.
Maybe I have a question. Do you know any way to compute characters of these representations that you described in terms of framed quivers? These type of Nakajima quiver varieties. The examples you gave were usual Nakajima quiver varieties, but then presumably for a quiver and arbitrary potential, you have other types of Nakajima type quiver varieties arising.
Let me see. So you mean if I have a Q tilde, W tilde, and then so let me see if I understand.
So in the cases, the real 3D cases, not the 2D cases, the new 3D cases, is there a way to compute character of the representations in this framed quiver varieties?
Yeah, I didn't think about that. So what would be an interesting example, like the one I described?
No, but this upgrade of our work, for example, with Rabchak, Yang, and Zhao, when you have not just one framing vertex, but three framing vertices, one between any two of three loops of your quiver Q3, and pairs of opposite arrows, like, like imagine Nakajima quiver, two loops and one framing vertex and two opposite things, and now you have three loops, and between any of two of them you have this Nakajima type of picture. It's very symmetric. It's you have these three so we did it for cohomological whole algebra, but probably you can easily do it for K-theoretical.
Yeah. In this example, right?
So but what would be an interesting example, Olivier, of
I don't know. I don't know.
Okay.
Just wondering.
Yeah, I didn't think about that.
New families of quiver varieties.
I see. Okay.
And maybe a very naive question. You talked about this MD category.
Yes.
Cuspidal, counting cuspidal.
Yeah.
Is there any hope that this can be the derived category of coherent sheaves on something?
No, I don't think so. Yeah, because that thing, if it is the category of something, let me see. I think so. The periodic cyclic homology of these categories MD, they recover intersection homology of the stacks XD. But then, so this will mean that maybe the stacks XD. So if what you're saying is true, the stacks will have a resolution Y, like a geometric resolution Y, which is small, or so that when we apply the decomposition theorem, we get that the cohomology of Y is the same as the intersection cohomology of XD. But so Spenko and Vandenberg in their paper, they look at some examples of singularities of the spaces. And I think they have a comment that usually it's not known that they have this nice geometric resolutions.
Okay.
So I don't think it's true.
Yeah, and maybe one stupid question. Your algebra is K0 of some category, it acts on K0 of some other category. Can you categorify this result? The category acts.
Yes, yeah, I think that's not hard.
Yeah, probably just a product will be given by some kernels, categorical kernels, yeah.
Yes.
Okay, thank you.
And just to understand, so you have these two theorems, the category acting like there was one in the two-dimensional picture and one in the three-dimensional picture. So you said that there was a action involved. So using Nakajima quiver varieties and how this kind of do this construction produce the same answer in a sense. So on the previous page you had identification between K-theoretic algebras. Yes, so I'm talking about, so there's a natural representation constructed using framings, and then another one is using Nakajima quiver varieties. On the previous page, I guess you were talking about identification of algebras, and are these different? Yes. So these are kind of...
No, I think these are the same. It's like the positive part of quantum groups, right? That acts on Nakajima quiver varieties. So I think this was done by Olivier and Bassereau, and it should correspond to what Maulik and Okounkov did. I don't think they are new representations.
But again, so these two theorems, the representations constructed in these two ways, they are related, right?
Yeah, so I split it in two parts just to highlight some important examples. But so in the paper, what I have is that I have a quiver QW, and then I take a larger quiver Q prime, and then I deform the potential to a potential W prime in there. And then the theorem is that the KHA for the smaller pair will act on things like this, like K0 of some stuff that comes from the larger quiver plus a stability condition.
Mm-hmm. And in the second theorem, the construction is different in the...
so in the first theorem, what we start with our quiver Q3, and the larger quiver is this one that I drew here, with only one new arrow. So, but in order to get the representations with Nakajima quiver varieties, what we do is, so we put one here, but we add three new edges, this I, J, and T. And then this whole framework will say that the K-theory, the KHA on Q3, W3 will act on the direct sum of K0. And here I have some categories of singularities for this X1D semi-stable 0, where now 0 is for this potential, which is XYZ minus XZY plus TJI.
Yeah, I have just a small comment that exactly this potential appeared in our paper with Diaconescu, Kryojcik, and Chuang. And it's, but we fix a conjugacy class of T. It's sort of, it's not a variable like in your story, but it's rather some fixed coefficient. And it's related to the Hilbert scheme on the fat divisor. You take like C square and C cube, and the C square you take with certain multiplicity, non-zero multiplicity, actually bigger than 1, some fixed multiplicity, and you consider Hilbert scheme on this fat divisor. And so then probably your K-theoretical Hall algebra acts on the cohomology of this fat Hilbert scheme exactly like, excuse me, in the K-theory of that scheme as in the case of cohomology we did. Yeah, so it's nice. It has some physical meaning actually.
But so to finish with Roman's question, and now with these categories of singularities, we can use dimensional reduction once again and say that they will be equivalent to coherent sheaves on Hilbert's scheme of points on A2.
Thank you.
Yeah.
Are there any other questions?
One more question. Sorry.
Yes.
Do you expect the representations in this first theorem to extend to the Drinfeld double?
Yeah, I don't have an expectation.
Do you have the notion of Drinfeld double?
No, I also don't have that.
Actually, in the case of cohomology, what's happened that you mentioned this problem with the co-multiplication, which kind of, if you do it naively, it has some poles. But if you go to the spherical subalgebra, which you can do in the case, then this co-multiplication doesn't have poles. And so you have an honest Hopf algebra and you can do Drinfeld double. But I don't know as for K-theory.
But I guess in Yangians, they have a paper.
Yeah. That's what we did.
Okay.
Yeah, exactly.
Just another quick question. So in the very end, in the proof of PVW theorem, so you said that this category M bar is very like explicit. About the category M in the beginning.
Yeah, so M is a little trickier to define because the issue is that this category M bar will still have complexes which come from multiplication from smaller dimension vectors. So also you can see here in this polytope that we don't exclude the boundary. So what will happen is that on this category MD, MD bar, we also, in order to define MD, so MD will be a subcategory of this, we need to impose some conditions when we restrict to the boundaries of this polytope. So it will be a restriction to some categories like let's see one. Well, let's see if this works. Yeah, so it's a little harder to define. It's definitely not as nice as M bar.
But do you at least know like the size of K-theory of MD or?
You mean in some examples? Or?
I mean in general, like can you compute how many generators are there, or it's just
so,
like, you know?
For example, in a type A, this is possible, or in the Jordan quiver case, it's possible. I think in general, this K-theoretic, K0 of MD or of MRD, they'll be infinite dimensional for a generic potential.
But for instance, for Jordan quiver, you can recover like the analog of this computation of Kapranov-Fastrov, like where they compute the size of the thing.
Okay, so I didn't know they do that, but it's the analog of what Davison and Meinhardt do in cohomology, where they see that the dimensions of generators in each dimension is 1. Yeah, you can recover that.
Thank you.
Okay, well, let's thank this. Or was there one more question? Sorry?
No, just a question whether it's in the archive or what's the status?
Yes.
It's all in your big paper, yeah?
Yes.
Okay, thank you.
Yes.
Okay, great. Let's thank the speaker again and all the speakers this day.